Hello everyone. In this question, it is given that we are to find the value of the greatest integer function of the summation of 1 upon n plus 1 times square root of n as n goes from 1 to infinity. Okay, so we are given a function which is 1 upon n plus 1 times square root n. Okay, we will do the summation later on. Let us see how we can simplify this value further. Okay, so first of all, let me try to multiply this numerator and denominator with the square root of n. Okay, so then this becomes square root of n times n plus 1, and this square root of n times square root of n will become n, right? Okay, so now I can write it like square root of n times 1 upon n plus 1 times n. Okay, now this can be further simplified as n plus 1 minus n in the numerator. Okay, and I'm keeping the denominator as it is for the time being. Okay, so now if I do the partial splitting here, partial fraction here, this becomes 1 upon square root n times 1 upon n minus 1 upon n plus 1, right? Okay, and this is multiplied with square root of n. Okay, so if I now separately multiply each of these terms with square root of n, this becomes 1 upon square root of n minus square root of n upon n plus 1, right? Okay, so now we are given the sum as n goes from 1 to infinity, right? N is a positive, say positive natural number for the time being. Okay, positive natural number here. So we can say that this will 1 upon root n minus root n upon n plus 1. This value, which is the function here, okay, this value is greater than 1 upon root n minus square root n plus 1 upon n plus 1, right? Here we are subtracting a larger quantity. Square root of n plus 1 is larger than square root of n, right? The first term is same in both sides, but this square root of n upon n plus 1, this is a smaller quantity and this is a larger quantity, right? So this implies that basically since n is positive, this is of the form say 10 minus 3. This value 10 minus 3 is obviously greater than the value of 10 minus say 5, right? So in this case, this is the smaller number here and this is the larger number. So since n is positive, this difference has to be greater than this difference, right? Since this second term, we are subtracting a larger term here. Okay, so this is what I have done here. Now this further implies that 1 upon root n minus root n upon n plus 1, this value is greater than 1 upon root n minus this value on simplification becomes 1 upon root n plus 1, right? Right, so far so good. Okay, so now the left hand side, this is nothing but the original function, right? On simplifying this original function, we have deduced this, right? This is the left hand side of this inequality. Okay, so I can substitute this value here also. Okay, so this gives us 1 upon n plus 1 times square root n is greater than 1 upon root n minus 1 upon root n plus 1. Okay, so now I can find the summation of this both sides. Okay, so on taking the summation from 1 n equal to 1 to infinity, the inequality will still hold, right? So this now becomes n goes from 1 to infinity, 1 upon square root of n minus 1 upon square root n plus 1. Okay, so this gives us summation n goes from 1 to infinity, 1 upon n plus 1 times square root n is greater than, if I start putting the values here, 1, the first term will be 1 upon square root of 1, right? So first value is 1. Second value, on putting n equal to 1 here, it will become 1 upon root 2, right? Similarly, on putting root 2 here, this will become 1 upon root 2 plus. Then next term, on putting n equal to 2 here, it will become 1 upon root 3. And the term after that, on putting n equal to 3 here, this will become 1 upon root 3. So you see these terms are getting cancelled here, right? And this goes on until we put n equal to infinity here. So the last two terms, on putting n equal to infinity in the denominator, this will become 1 upon infinity. So this will become 0. The last term also, infinity plus 1 again is infinity. So 1 upon infinity will be 0, right? So we are only left with 1 here, as these terms will cancel each other, right? So we are left with this summation as n goes from 1 to infinity, 1 upon n plus 1 times square root of n is greater than 1, right? Okay, so this is, say, equation 1. Okay, we have to find the greatest integer value, and we have found that the sum is greater than 1. Okay, it is strictly greater than 1. So we have done the upper bound here, sorry, lower bound here. Okay, lower bound here, this is more than 1. Okay, so now let us find the upper bound here. Okay, again the function was 1 upon n plus 1 times square root of n, right? So this can be further written as root n plus 1 times root n times root n plus 1 upon 1, right? I have multiplied this 2 times. If you multiply this square root n plus 1 2 times, you get n plus 1, right? So now if I introduce a 2 in both numerator and denominator, then this will become 2 upon square root n plus 1 upon square root n, and I'm introducing a 2 in this term here. Okay, so this 2 and this 2 eventually cancel each other. Okay, so I'm multiplying and dividing the fraction by 2. Okay, so this now can be written as 2 upon square root n plus 1 times square root n, and this 2 times square root n plus 1, I can write it as the summation of summation 2 times, right? 2x can be written as x plus x. So I am writing this 2 times this square root n plus 1, square root n plus 1 plus square root n plus 1. Okay, I am writing this term here, this third term here, as a sum of 2 square root n plus 1. Okay, now this was the original function, right? So now this value 2 upon square root n plus 1 times square root n times the summation square root n plus 1 plus square root n plus 1. This will be less than 2 upon square root n plus 1 times square root n times square root n plus 1 plus square root n. Okay, see this term up to here, these two are identical, right? The difference is here in the denominator I am adding a larger number here. Again, see, compare this number and this number here, right? This is like 3 plus 3 and this is 3 plus 2 in the denominator. Okay, so adding a larger number in the denominator will reduce the value of the fraction, right? Okay, this is larger here, and this term, this third term, this is smaller, right? So since the smaller number is added in the denominator, this value of the fraction will be overall larger, right? Simple. Okay. So on further simplification, this 2 upon this is nothing but the original function, right? 1 upon this original function. So I can write it as the original function. 1 upon n plus 1 times square root n. This is less than, this is 2 upon square root n plus 1. So if I write 2 separately, I can write this 1 as n plus 1 minus n, and I'm keeping this other part as it is, okay, in the denominator. Square root n plus 1 plus square root n. Sorry, this is square root n in the denominator of the first of the left hand side. Okay, so this can be further simplified as root n plus 1 whole square minus square root of n whole square in the numerator, right? This is n plus 1 minus n, so I can write it as square root n plus 1 whole square. So this square and root will cancel each other, and similarly for this term also. Okay, and this in the denominator I'm not changing anything, I'm keeping it for the time being as it is. Square root n plus 1 plus square root n. So this now gives us 2 times, this will be of the form a plus b into a minus b, right? A square minus b square. So this becomes n plus 1 plus square root n times square root n plus 1 minus square root n. So we see that we can cancel this square root n plus 1 plus square root n in that numerator and denominator, right? Okay, so we can cancel these two terms. So this now gives us 1 upon n plus 1 times square root n will be less than 2 times, we are left with square root n plus 1 minus square root n upon square root n plus 1 times square root n, right? So again, like we did in this here, we separated the partial fractions here. Okay, again we will separate these fractions separately. So this will give us 1 upon n plus 1 times square root n is less than 2 times this, on separation this term and this term will cancel each other, so we are left with 2 times 1 upon root n minus 1 upon root n plus 1. Okay, so now we can use the summation here. Summation n goes from 1 to infinity 1 upon n plus 1 times square root n is less than, since 2 is a constant, this can be taken outside the summation, and this becomes 2 times summation as 1 goes from infinity 1 upon root n minus 1 upon square root n plus 1. Okay, so this is almost completed now. 1 upon n plus 1 times square root n will be less than 2 times. Again, we will start putting the values here. So on putting the values of n equal to 1, this will become 1 upon root 1. So this is 1. Again, this term on putting n equal to 1, this will become 1 upon root 2. And the term after that will be plus 1 upon root 2 minus 1 upon root 3. And then after that it will be plus 1 upon root 3. And this will go on. until we put the value of n equal to infinity, which will give us plus 0 minus 0 again. So these terms again cancel each other like it did in the previous part also. Okay, so now we are left with this summation 1 upon n plus 1 times square root n is less than, we are only left with 1 inside the bracket, right? And 2 is outside the bracket, so it's 2 times 1, so this is 2. So we see the sum is less than 2. Okay, this is equation 2, equation 2 here. So from equation 1 we had the sum was greater than 1, and from equation 2 here we see the sum is less than 2. Okay, so from equation 1 and 2 we get that 1 is less than the sum as n goes from 1 to infinity 1 upon n plus 1 times square root n, and this is less than 2, right? Now the question was to find the greatest integer value of this sum. Okay, so we don't know the exact value of this sum, but we have to find the greatest integer value. So this implies the greatest integer value of this sum as n goes from 1 to infinity, the greatest integer value, since this sum lies between 1 and 2, so the value of the sum will be say 1.6, 1.7, 1.8, 1.4, something like that. So the greatest integer value of such 1.6 or 1.7 is 1, right? So this is the required final answer. Okay, we have to show that the lower bound of this sum is 1 and the upper bound is 2. Okay, so this was the method I used for doing this, for finding this greatest integer function. Okay, so there was a lot of algebraic manipulation required here, especially in while finding the upper bound here. Okay, so this was a bit tricky, bit difficult, bit lengthy, all things considered. Okay, so if you have any doubt in any part, any step, you can highlight in the comments. Okay, this required some time, some effort in order to find this value. Okay, so if you have any doubt, you can highlight in the comments also. If you have any better methods also, you can highlight in the comments. Okay.